right? So when we look at differentiability, I'm talking about skimmable. It can slide. So let's say I have a function like this. Could you imagine being on like a roller coaster or on roller skates or on a board that could just skim right along there? That's what we call differentiable, skimmable. What happens if we have a curve that has a jump discontinuity on it? How skimmable is that? Radical. That would be kind of fun that way. In the book, though, he tries to skim over something like this, and there's an even greater gap in that jump discontinuity, and so he loses his board, which he's really just very sad about. I don't know if he cries or not. I don't think 9-year-old boys cry, do they? Yeah, they probably do. But anyway, he loses his board because it's non-skimmable. What's another way that something is non-skimmable, but it's still continuous? Do you remember that? Remember a shape that was non-skimmable? Point discontinuity? Well, a point discontinuity, you could skim that probably. Aha, yeah, it's called a cusp. A cusp. What it's continuous. It's continuous, but what's non-skimmable about it? Think of that kid on a little hoverboard. Can't get over that peak because the slope on the left and the slope on the right, how do those compare? They're not equal. And this is what we would call non-differentiable too. So the two conditions, and they laid it out really nicely right here, is that you either can't skim it because it's not continuous at A, or if the slope on one side is different than the slope on the other. If those slopes don't line up, it's not skimmable. It's not differentiable. The classic is f of x equal absolute value of x. Is there anything I can't put in for x? No, it's fine. You can it's continuous. So if you draw your finger along the absolute value of x, you'll get a nice V shape. But what if you tried to skim this? You'd run aground at 0, right? Your board would smack into that and you'd be done. Because what is the slope on the left of 0? -1. What's the slope on the right of 0? +1. So these are different, and so we would say non-skimmable or non-differentiable. So let's take one that's a little bit more complicated. By the way, let me review real quickly the slope idea. Slope is a change in y over change in x, and we can write that with f of a plus h minus f of a, which is a difference in y's over a difference in x of h. So that's where that notation comes from. We're going to take one that makes a little bit more sense. We're going to prove that this is continuous. So how would you show that this equation is sine x when x is greater than 0? Okay, that function is going to be continuous to this one. By the way, this is going to be a parabola that goes through -5 and 0. So is this continuous? How do you know if it's continuous? What is the limit as x approaches 0 from the left of x squared plus 5x? Put a 0 in. What do you get? X squared plus 5x when x is 0? 0, right? What's the limit as x approaches 0 from the right of sine x? What's the sine of 0? 0. So these are the same. What can you tell me about continuous? Is it continuous at 0? Continuous at x equals 0, because the left limit is 0, the right limit is 0. Are you okay with that? So how do we know if it's skimmable or differentiable? What do we have to do? take the derivative. Do you remember the derivative of sine of x? Been a while. Do you remember? It is the cosine of x. We will prove that in a moment. What is the derivative of x squared plus 5x? Very nice. Okay. Now I'm going to analyze this when x is equal to 0. So f prime of 0 is going to be the 0 plus 5. 5. So the slope on the left is 1, and the slope on the left is 5. The slope on the right is 1. Is this differentiable? Non-differentiable at x equal to 0. It's because the slope on the left is different than the slope on the right. So that's differentiability.